So good day everyone. I am one of the members of Group 3. I am Kimberly Sabal from BS Ed Science 12A. And today I'm going to discuss my topic, which is fluid dynamics and Bernoulli's principles. So let's start first in fluid dynamics. But before we start to the discussion, let's find out the relationship of fluid kinematics, fluid dynamics, and fluid statics. So we all know already no na fluid kinematics was already been discussed by the previous reporter. And now, what is fluid kinematics? So fluid kinematics, it deals with motion of the fluid without considering the factors that are affecting the motion, while fluid dynamics, it is focuses on the factors that are affecting fluid motion, and fluid statics deals with the response or behavior of the fluid when it is at rest. So, um, the relationships, they are just connected with each other because they are talking about flows, when flows in motion and flows when at rest. So now, what is fluid dynamics? So fluid dynamics is an area of applied science concerned with the movement of the liquid and gases. It is according to the American Heritage Dictionary. So fluid dynamics is one of the two branches of fluid mechanics, which is the study of fluids and how their strength affects them. So fluid dynamics is a subdiscipline of fluid mechanics that deals with fluid movement in motion. So there are several branches of fluid dynamics. Two of them is aerodynamics and hydrodynamics. We'll be going to discuss the two subdisciplines of fluid dynamics later. So now we have here the two subdisciplines of fluid dynamics, the aerodynamics and hydrodynamics. So when we say aerodynamics, the study of air and other gases in motion. So the term aerodynamics is often used synonymously with gas dynamics. The difference being that gas dynamics applies to the study of the motion of all gases and is not limited to air. So the formal study of aerodynamics began in a modern sense in the 18th century, although observations of fundamental concepts such as aerodynamic drag were recorded much earlier. Now we have here the second one, the hydrodynamics. So it is the study of liquids in motion. So as you can see in the picture, it is the study of liquids such as water in motion. So now we have here flow. So the term that physicists use to describe the physical properties of the movement of liquid. So since fluid dynamics involves the study of the motion of liquid, one of the first concepts that must be understood is how physicists quantify that movement. So the term that physicists use to describe the physical properties of the movement of liquid is called flow. So flow describes a wide range of fluid movements such as blowing through the air, flowing through a pipe, or running along a surface. The flow of fluid is classified in a variety of different ways based upon the various properties of the flow. So we have here the properties of the flow. We have here the first, the steady versus the unsteady flow. When we say steady, if the movement of flow does not change over time, it is considered a steady flow. So this is determined by the situation where all properties of the flow remain constant with respect to time, or alternately can be talked about by saying that the time derivatives of the flow field vanish. The second one, that steady flow. If the properties of the fluid itself change at some point, it is considered as unsteady flow. So this is opposite of the steady flow. Now we have here the next, the laminar flow and versus turbulent flow. So a laminar flow, a smooth flow of liquid is said to have laminar flow. Flow that contains seemingly nonlinear motion is said to have turbulent flow. Now we have here the pipe flow versus open channel flow. So pipe flow represents a flow that is in contact with rigid boundaries on all sides. So such as water moving through a pipe or air moving through an air duct. When we say open channel flow, describes flow in other situations where there is at least one free surface that is not in contact with a rigid boundary. So cases of open channel flow include water moving through a river, floods, water flowing during rain, tidal currents, and irrigation canals. Now we have here compressible versus incompressible. So compressible fluid is one in which the fluid density changes when it is subjected to high pressure gradients. So an incompressible fluid is a fluid which is not compressed or expanded, and its volume is always constant. So as you can see in the picture, we have here the liquid, which is a incompressible fluid, while the gas as a compressible fluid. Now let's proceed to the applications of fluid dynamics. So 2/3 of the Earth's surface is water, and the planet is surrounded by layers of atmosphere. So we are literally surrounded at all times by fluids, almost always in motion. So here are the following applications of fluid dynamics. We have here the oceanography, meteorology, and climate science. Since the atmosphere is modeled as fluids, the study of atmospheric science and ocean currents, crucial for understanding and predicting weather patterns and climate trends, relies heavily on fluid dynamics. Now we have here the aeronautics. The physics of fluid dynamics involves studying the flow of air to create drag and lift, which in turn generate the forces that allow heavier than air flight. Next, we have geology and geophysics. So plate tectonics involves studying the motion of the heated matter within the liquid core of the Earth. We have here hematology and hemodynamics. So the biological study of blood includes the study of its circulation through blood vessels, and the blood circulation can be modeled using the methods of fluid dynamics. Now we have here the plasma physics. Though neither a liquid nor a gas, plasma often behaves in ways that are similar to fluids, so can also be modeled using fluid dynamics. Now we have here the astrophysics and cosmology. So the process of stellar evolution involves the change of stars over time, which can be understood by studying how the plasma that composes the stars flows and interacts within the star over time. Now we have here the traffic analysis. So perhaps one of the most surprising applications of fluid dynamics is in understanding the movement of traffic, both vehicular and pedestrian traffic. In areas where the traffic is sufficiently dense, the whole body of traffic can be treated as a single entity that behaves in ways that are roughly similar enough to the flow of a fluid. Now let's proceed to Bernoulli's principle. So why do we need to learn Bernoulli's principle, and what was the connection of this in fluid dynamics? So Bernoulli's principle, sometimes also called the Bernoulli effect, is one of the most important results in study of fluid dynamics. So relating the speed of the fluid flow to the fluid pressure. So this might not seem particularly important, but as the huge range of phenomena it helps to explain shows, the simple rule can reveal a lot about the behavior of a system. So fluid dynamics is the study of moving fluid, and it so makes sense that the principle in its accompanying equation, which is Bernoulli equation, comes up quite regularly in the field. So Bernoulli's principle. So as what I have said earlier, Bernoulli's principle, sometimes also called the Bernoulli's effect, is one of the most important results in study of fluid dynamics, relating the speed of the fluid flow to the fluid pressure. So the principle relates the fluid pressure and its speed and elevation, and it can be explained through the conservation of energy. So Bernoulli's principle: within a horizontal flow of fluid, points of higher fluid speed will have less pressure than points of slower speed. So within a horizontal water pipe that changes diameter, regions where the water is moving fast will be the water is moving slow. So they sound counterintuitive to many people, since people associate high speeds with high pressure. Now let's talk about how can you derive Bernoulli's principle. So incompressible fluids have to speed up when they reach a narrow constructed section in order to maintain constant volume flow rate. So if the water is speeding up at a construction, it's also gaining kinetic energy. So the only way to give something kinetic energy is to do work on it. So this is expressed by the work energy principle. Work external equals delta Q equals 1/2 mass final volume squared equal minus 1/2 mass initial volume squared. So that's the work energy principle. So if a portion of fluid is speeding up, something external to that portion of fluid must be doing work. So what force is causing work to be done on the fluid? So consider the diagram below here. The diagram below, which shows water flowing along streamlines from left to right. So as the outlined volume of water enters the constructed region, it speeds up. So the force from pressure 1 on the left side, as you can see the picture of the shaded water, pushes to the right and does positive work since it pushes in the same direction as the motion of the shaded fluid. So the force from pressure 2 on the right side of the shaded fluid pushes to the left and does negative work since it pushes in the opposite directions the motion of the fluid shaded fluid. So the pressure 1 and the pressure 2 is inversely proportional. So now let's proceed to what is Bernoulli's equation. So Bernoulli equation is essentially a more general and mathematical form of Bernoulli's principle that also takes into account change in gravitational potential energy. So we'll derive this equation in the next section, but before we do, let's take a look at Bernoulli's equation and get a feel for what it says and how we'd go about using it. So Bernoulli's equation relates the pressure, speed, and height of any 2 points in a steady, streamlined flowing fluid of density. So Bernoulli's equation is usually written as pressure 1 plus 1/2 density volume 1 squared plus density height GH 1 equals pressure 2 plus 1/2 density volume 2 squared plus PGH 2. That's density and height 2. So the variables P1 and V1 height refers to the pressure, speed, and height of the fluid at point 1. The variables P2, V2, height 2 refers to the pressure, speed, and height of the fluid at point 2. So the diagram below shows one particular trace of 2 points 1 and 2 in the fluid, but Bernoulli's equation will hold for any 2 points in the fluid. So when using Bernoulli's equation, how do you know where to choose your points? So note that h refers to the height of the fluid above the arbitrary level. So typically, it is often easiest to just choose the low of the 2 points 1 or 2 as the height, where h height equals 0. So the P pressures refer to the pressure at the point. You can choose to use gauge pressure or absolute pressure, but whichever kind of pressure you choose, gauge or absolute, must also be used on the other side of the equation. So the term 1/2 P density volume squared and PGH in Bernoulli's equation look like just like kinetic energy. So 1/2 mv2 and potential energy mgh, only with the mass m replaced with density p. So now how do you derive Bernoulli's equation? So consider the following diagram where water flows from left to right in pipe that changes both area and height. So as before, water will speed up and gain kinetic energy key at constructions in the pipe, since the volume flow rate must be maintained for an incompressible fluid even if those construction sections move upward. But now, since the construction also causes the fluid to move upward, the water will be gaining gravitational potential energy UG as well as kinetic energy K. So we will derive Bernoulli's equation by setting the energy gained by the fluid equal to the external work done on the fluid. So then any extra energy, delta K plus U, system added to the system will be caused by the external work external done on the fluid from pressure forces surrounding it. So we will derive into work external cos delta K plus U system. So work can be found with work equals Fd. We can plug in formula for the force from pressure F equals PA into the formula from work to get work equals PAD. So the positive work done in our system by the water near point 1 will be work 1 equals P, pressure 1, area 1, and density 1, and the work done by the water near point 2 will be work 2 equals negative pressure 2, area 2, and density 2. So plugging these expressions for work into the left side of our work energy formula, work net equals delta K plus U system, we get pressure 1, area 1, density 1, minus pressure 2, area 2, density 2 equals delta K plus U system. So, but the terms A plus 1 D1 and A plus A2 D2 have to be equal since they represent the volumes of the fluid displaced near point 1 and point 2. If we assume the fluid is incompressible, an equal volume of fluid must be displaced everywhere in the fluid, including near the top. So how does the idea of steady flow help us figure the change in the energy of the big winding system of fluid? So consider the diagram below. Our energy system consists of the grayed out fluid, volume 1, volume 2, and all in fluid in between. So in the first image, the system has some amount of total K plus U initial. In the second image, the entire system had work done on it, gains energy, shifts to the right, and now has some different total energy K plus U final. But notice that the energy of the fluid between the dashed lines will be same as it was before the work was done, assuming steady flow. Water changed position and speed in the region between the dashed lines, but it did so in such a way that it will be moving with the exact same speed and have the same height as the previous water had in that location. The only thing that's different about our system is that volume 2 now extends into a section of the pipe it wasn't in previously, and now nothing in our system is occupying the old position behind volume 1. So overall, this means that the total change in the energy of the system can be found by simply considering the energies of the endpoints. Namely, we can take the kinetic and potential energy, K2 plus U2, that now exists in volume 2 after the work was done, and subtract the kinetic and potential energy, K1 plus U1, that no longer exists behind volume 1 after the work was done. In other words, delta K plus U system equals K2 plus U2 minus K1 plus U1 since we subtract the kinetic and potential energy. So plugging this into the right hand side of the work energy formula, pressure 1 volume minus pressure 2 volume equals delta K plus U system. We get pressure 1 volume minus pressure 2 volume equals K2 plus U2 minus K1 plus U1. So now we'll substitute the formulas for kinetic energy. So K equals 1/2 m mass volumes 2, and gravitational potential energy equals UG equals mgh to get pressure 1 volume minus pressure 2 volume equals 1/2 mass 2 V2 squared plus mass 2 gravitational potential energy height 2 minus 1/2 mass 1 volume 1 squared plus mass 1 gravitational potential energy height 1. Now we can divide both sides by V and drop the parentheses to get. So we have here P1 minus P2 equals 1/2 mv2 squared over V plus mgh 2 over V minus 1/2 mv1 squared over V minus mgh1 over V. So we can simplify this equation by noting that the mass of the displaced fluid divided by volume of the displaced fluid is the density of the fluid equals mass over volume. So replacing V with density or P, we get P1 minus P2 equals 1/2 PV2 squared plus PGH2 minus 1/2 PV21 minus PGH1. So now we're just going to rearrange the formula using algebra to put all the terms that refer to the same point in space on the same side of the equation to get pressure 1 plus 1/2 PV21 plus PGH1 equals P2 plus 1/2 PV2 squared plus PGH2. So and there it is. Finally, this is Bernoulli's equation. It says that if you add up the pressure plus the kinetic energy density, 1/2 PV2 plus the gravitational potential energy density PGH at any 2 points in a streamer, they will be equal. Now, let's talk about how is Bernoulli's principle a result of Bernoulli's equation. So we should note here that Bernoulli's principle is contained with Bernoulli's equation. So P1 plus 1/2 PV1 squared plus PGH1 equals P2 plus 1/2 PV2 squared plus PGH2. And assume that there is no change in the height of the fluid. The PGH terms cancel if you subtract them from both sides. So P1 plus 1/2 PV1 squared equals P2 plus 1/2 PV2 squared, or we could write it as a pressure plus 1/2 density volume squared. So this formula is a constant. So this formula highlights Bernoulli's principle, since if the speed of a fluid is larger in a given region of streamline flow, the pressure P must be smaller in that region. So an increase in speed V must be accompanied by a simultaneous decrease in the pressure P in order for the sum to always add up to the same constant number. So I have here the sample problem. Let's compute them. So I have here the example. You own a restaurant that is investigating new ways to deliver beverages to customer. One proposal is for a tube that will deliver root beer of density 1090 kg cubic meter throughout the restaurant. A section of the tube is shown below. The blueprint says that the speed and gauge pressure of the root beer at point 1 are 3 meter per second cubic second and 12,300 respectively. So the root beer at the point 2 is 1.20 meter higher than the fluid at point 1 and is traveling at a speed of 0.750 meter per second. You can make out the number on the blueprints for the pressure of the root beer at point 2. So we need to find here the pressure 2. So here's the solution. So first, start with Bernoulli's equation, which is pressure 1 plus 1/2 PV1 squared plus PGH1 equals pressure 2 plus 1/2 PV2 squared, plus PGH2. And algebraically solve Bernoulli's equation for pressure 2. So we're going to use this formula. So pressure 2 equals pressure 1 plus 1/2 PV1 squared plus PG. The height is 0 meter minus 1/2 pressure density velocity 2 squared minus PG. The height is 1.2 meter. So we plug in the values of H1 and H2. So pressure 2 equals, the pressure 1 is 12,300 PA plus 1/2. We have the density of 1.090 kilogram cubic meter and the velocity of 3.0 meter second squared minus 1/2 and the density 1090 kilogram cubic meter times the velocity 0.750 meter second squared minus the density again 1.090 kilogram cubic meter times G times the height 1.20 meters. So we will derive this answer. The pressure 2 equals 4080 PA. And that's all my topic. I'm gonna summarize my topic from fluid dynamics. So fluid dynamics, when we say fluid dynamics, it is the study of the movement of the fluids, right? And there are two subdisciplines of fluid dynamics, which is the aerodynamics, it is study of gases in motion, and hydrodynamics, the study of fluid in motion. And the applications we also listed some applications there, and of course the Bernoulli's principle that it's very important to study because it's connected to fluid dynamics. And the Bernoulli's equation that has a formula of pressure 1 plus 1 half density volume 1 squared plus density g height 1 equals pressure 2 plus 1 half density volume 2 squared plus density g h 2. And that's the constant of the equation for Bernoulli equation is pressure plus 1 half density volume squared, and that is a constant formula of Bernoulli's principle. That's all. I hope you've learned something about today's discussion. Thank you, and God bless you. So hello, so this is the proper calculations of the sample problem I have given earlier in the PPT. So I'm gonna show you guys how to solve this in a proper way. So I have here the given. We have here the pressure. Ang atong pangitaon is the pressure 2, right? So the pressure 1 is 12,300 PA. The density is 1,090 kilogram meter cubic. Velocity 1, we have 3 meter per second cubic second. The velocity 2 is 0.750 meter second. Height 0 meter, and height 2 1.2 meter. So we're gonna use the Bernoulli's equation. I mean the Bernoulli's principle. So we have here the P1 plus 1 half PV21 plus PGH equals P2 PV22 plus PGH2. So we're gonna substitute this. We have the P1. We're gonna arrange then in our algebraic. We're gonna arrange this algebraically. So we have here the P1 plus 1 half PV 1 plus PGH minus 1 half PV 2 minus PGH 2. So we're gonna solve this. We have here the P2. So that's the P2 equals P1 plus 1 half PV21 plus PG. Our height is 0 meter, height 1, and minus 1 half PV22 minus PG, and height 2 is 1.2 meter. Now we're gonna substitute this. P2 equals, or P1 is 12,300 PA, and plus 1 half, and the density is 1.090 kilogram cubic meter, and times, we have here 3.00 ms cube sa velocity 1, minus 1 half again, and then the density 1090 kilogram cubic. Then times 3, and then times the height 2 is 1.2 meter. So we're gonna solve this. You can use calculator to solve this given. So we're gonna derive the answer P2 as 4,080 PA. So that's the answer of the sample problem earlier I had given to you guys. So here.